Today we explore DLM, a proposal for language generation that asks a simple but disruptive question. Does text always have to be generated one token at a time, from left to right? The paper argues for a different route. Instead of making the surface token sequence the main state of generation, it first builds a continuous latent representation of meaning, then turns that representation back into text. Autoregressive language models are powerful because they give a clean objective: predict the next token. But that strength comes with a built-in constraint. Generation is inherently sequential, and the model is always biased toward one fixed ordering of tokens. Discrete diffusion models relax the order, but often require many denoising steps in token space. Continuous token space diffusion adds geometry, yet still often treats generation as recovering a token-aligned representation. DLM tries to combine the best parts while avoiding these bottlenecks. The core probabilistic idea is compact. A text sequence is generated through a hidden continuous variable. First, a prior creates the latent variable. Then a decoder realizes the final text conditioned on that latent. This separates two jobs that are entangled in standard token prediction, organizing global meaning and producing local wording. The encoder is used during training to infer latents from real text, but the actual generative model is the prior plus the decoder. DLM uses diffusion differently from many text diffusion models. The diffusion or flow process is not trying to gradually recover corrupted tokens. Instead, it transports a simple Gaussian noise sample into a meaningful latent semantic sample. In other words, diffusion is used as a prior over compressed meaning. The text decoder then turns that latent plan into discrete words. This is the key shift. Diffusion is for latent prior transport, not token-level observation recovery. The workflow has two training stages and one inference stage. First, a text VAE learns a stable bridge between text and continuous latents, using reconstruction, masking, and regularization. Second, a block causal diffusion transformer learns the latent prior while the VAE can still adapt under controlled gradients. At inference time, a prefix is encoded, future latent blocks are generated, and the decoder produces the response. This gives parallelism within blocks while preserving causal structure across blocks. The theoretical objective explains why this decomposition matters. The average training bound splits into three terms: reconstruction quality, the amount of information stored in the latent, and how well the learned prior matches the aggregated latent distribution. This makes the model analyzable as a division of labor. The latent should carry useful global information, but not every surface detail. The prior should organize that latent space, while the decoder handles local linguistic realization. A central empirical question is whether the latent space really contains shared global semantic structure. The paper tests this through time-step shifts across different latent dimensions. If the latent coordinates were purely local and separable, the best shift should not drift systematically with dimension. But the experiments show a clear pattern. As dimension increases, the optimal shift moves to larger values, and this behavior is consistent across semantic benchmarks. That is evidence for shared structure in the latent space. The next lesson is that the latent space should not simply be frozen, but it also should not be learned from scratch without support. The strongest setting starts from a stable pre-trained VAE and then lets the latent space co-evolve with the diffusion transformer. Fixed latents help early stability but saturate. Training everything from scratch can collapse or form weaker geometry. The best results come from controlled co-adaptation between representation and prior. The diffusion transformer also needs the right granularity and noise calibration. A moderate block size, especially 16, gives the best balance between local grouping and causal structure. Too large a block weakens useful interactions, while a block size of 1 is competitive but less strong. The noise schedule also matters. A shifted schedule with location around 1 outperforms uniform sampling. In this framework, schedule tuning is best understood as calibrating how much semantic information remains visible at different denoising times. At inference time, the model does not need an extremely large number of denoising steps. The experiments show a sharp improvement from very few steps to around 8 or 16, followed by saturation. Because each block contains multiple tokens, this can reduce the sequential depth compared with token-by-token decoding. Guidance also has a sweet spot. Moderate classifier-free guidance improves semantic recovery, but excessive guidance distorts the trajectory and hurts performance. The headline result is the scaling comparison. Under a matched few-shot generative evaluation protocol, COLA-DLM shows strong scaling across 8 benchmarks and reaches the best final task average. The advantage is especially visible on reasoning-heavy and global semantic tasks such as MMLU, race, story close, and open book QA. The absolute scores on some multiple-choice tasks are conservative because all models must generate answers directly, but the relative scaling trends are the key message. One important caveat is that likelihood-oriented perplexity can be misleading for continuous latent models. Good generation only requires the prior to land in decoder-valid semantic regions. Likelihood estimation additionally demands precise local density calibration around the gold posterior latent. The paper visualizes this mismatch. Decoder recovery can be strong even when prior density alignment around the exact target is uneven. So for this model family, generation quality and scaling behavior may be more informative than perplexity alone. The broader takeaway is that COLA-DLM isn't just another denoising recipe. It is a proposal to represent text through a hierarchy, continuous global semantics first, discrete local realization second, that makes it modular, analyzable, and potentially extendable beyond text. The same latent prior idea can connect text and images by mapping each modality into continuous latents and modeling them with a shared prior. The open question is how far this paradigm scales with better latents, better priors, and larger compute.